In this video, I'll be answering a question related to long transmission line models, which was asked by one of my students during P-Power live training. Long transmission line models are probably the most complicated of the three. The other two are the short and medium transmission line models. And the reason for that is because they include hyperbolic trigonometric functions. In order to deal with these functions, I recommend my students to use Euler's Identity, which goes back to complex numbers from your FE electrical and computer exam preparation days. In my opinion, taking a purely mathematical equation or formula-driven approach will not help you much in your P-Power exam preparation. You have to learn concepts from first principles because that will allow you to deal with questions that are both conceptual and theoretical in nature and not just a numerical plug and check type of questions. So without further ado, let us dive into the content. Long transmission line hyperbolic trig functions. I recognize that the cosine hyperbolic, sine hyperbolic functions that we need to use, that we must use as part of long transmission line ABCD parameters cause quite a bit of confusion for students. And that's why in the study guide, I have at least a couple of problems that basically hammer on this point. Then I have gone through some additional practice problems in the on-demand course. I have specifically included some homework assignment problems in the live training. And that is all. That is basically an effort on my part to make you guys more comfortable. All right. So let's deal with this and use a mathematical approach to handle hyperbolic trig functions, not only for real numbers, but also for imaginary numbers. Now, my take on this is that I'm pretty sure that TI-36 actually is able to do this for you, but I want you guys to be comfortable calculating this by hand, okay? And the reason is pretty simple. On the P-Power exam, guys, you have plenty of time. 6 minutes per question. They're going to be questions, as you can see in the NC sample exam, some of which are just conceptual in nature, and it wouldn't take even 1 minute of your time, right? A lot of my students leave the exam with 1 to 2 hours to spare on the actual exam, okay? So let's learn it from first principles using Euler's identity. So the student is referencing study guide, second edition, problem number 8.9, and saying he was basically at it until 2:30 in the morning. And he reached out to me as like, okay, Wasim, can you please provide a stepwise approach on how to deal with it? And the issue is that when we are dealing with real numbers, the formula for cosine hyperbola or sine hyperbola, hyperbolic x, and cosine hyperbolic x is very simple. Because if I introduce a number in place of x over here, and this is minus x, then this is simply a number, right? Real number. It's simply an exponential. Exponential is 2.1718 raised to power whatever the number is. Are you guys following me? The issue arises when this x becomes a plus bj. All right, complex. So how do we deal with it in that case? Okay, and once you understand how to deal with it, it becomes so easy. Just remember that e raised to power I theta, Euler's formula, Euler's identity, is equal to cosine theta plus I sine theta. So when I have e raised to power a plus bj, can I write this as e raised to power a dot e raised to power bj? Yes? Any issues with this, guys? Okay. This is just a constant, a real number. I'm going to keep it as it is, and I'm going to explode e to the power of bj as cosine b plus j sine b. All good? And then it simply becomes e to the power a, which is a constant, remember that, multiplied by cosine of b plus j times e to the power a times sine b. You do not need to memorize any calculator trick or functionality to go from here to here. So regardless of whether they throw at you a real number or a complex number as part of this argument, as part of this function, you can very easily deal with it. Is this clear? The only other thing that I'm going to warn you to have a lookout for, to keep an eye on, is angle. If it's whether it's in degrees or radians. You guys know that whenever the angle has a pi by 2, pi by 3, we can right away categorize it as a degree or radian. Radian, correct? And degree would be explicitly mentioned as 30 degrees or whatnot. Okay, so keep that in mind. So now that we have all the tools that we need in order to deal with this, should be able to comfortably navigate any problem related to sine hyperbolic and cosine hyperbolic, which obviously will appear if you're tested on transmission line ABCD parameters. So just need to be careful. Okay. So this is my response to the student. So we are dealing with cosine. So he referenced 8.9W. Cosine hyperbolic gamma L. Now I can again, cosine hyperbolic function is e to the power of x plus e to the power of minus x. So you can see that e to the power of gamma L plus e to the power of minus gamma L divided by 2. Gamma L just building on top of what is already shown in the solution in 8.9W. Those of you guys who have access to this particular problem, you can pick it up from there. Our goal is to really understand the hyperbolic trigonometric functions in the context of long transmission line models. So this is actually equal to 0.16 plus 0.45J. So if I look at 0.16 as A plus 0.45 as B and then J, right? When I go back here, you can see my e to the power A, right, dot my e to the power of bj, right, which is 0.16 and 0.45. E to the power of 0.16, e to the power of 0.45j. Okay. Make sense? So unless mentioned otherwise, these numbers 0.45, you are going to interpret this as what? Radians. Okay. If you are explicitly given the angle in degrees, then you are going to consider that as degrees. Okay. So we know that e to the power of 0.16 is simply equal to a constant 1.173. And e to the power of 0.45j, notice that this is cosine B plus j times sine A. Cosine 0.45, sine 0.45. And then you can go about calculating these in radians. And then you have a constant 1.173 multiplied by this resulting factor, multiply it out. You have the rectangular form, then you have the polar form. And now you have actually determined e to the power e gamma L. And you can do the same thing in order to figure out e to the power of minus gamma L. Okay. When you're doing e to the power of minus gamma L, to the power of minus gamma L will be equal to e to the power of minus 0.16 plus 0.45j, which is going to be e to the power of minus 0.16 dot e to the power of minus 0.45j. So this is going to be a constant, and you're going to then explode this as cosine minus 0.45 plus j sine minus 0.45. Okay. Now there's more to long transmission lines, as we discussed in the on-demand. Long transmission lines, the beauty of long transmission line is that it applies to transmission lines that are 50 miles and above, right? Greater than or equal to, right? Now, it is interesting that it is able to keep the upper limit floating. How can it keep the upper limit floating? There's no upper limit, right? Because for the short transmission line, remember, we have 0 to 50. Then for medium, we have 50 to 150. And then for the long transmission lines, we have 150 to infinity. How is that possible? We discussed that in the course, right? That is possible because the long transmission lines use what we call incremental approach, the differential approach. So the length of the transmission line, the L, is actually incorporated in the equations. If you pull up the formulas for ABCD parameters, it is taking a differential approach. So as the length of the line increases, the formulas have a self-adjusting mechanism built into them. That is not true for short and medium transmission line models. Do you see any variable L in the ABCD parameters for short and medium? No, we don't. We simply take the parameters in and out. Okay. So the long transmission line models, whether you're dealing with a 150 mile or 1,000 mile or 2,000 miles, the hyperbolic functions are including the length, and that is helpful. And that's how we deal with it. Okay. So again, for a deeper review of transmission line models within section number 4, please review the on-demand content, lectures, quizzes, mini exams, study guide problems, and do ask yourself these deep questions, such as mathematically, how would this work? Okay, is there any other option? How can I do this in the calculator? But if you learn things from first principles, you will be set. And I have plenty of practice problems as well to help you deal with the numerical problems. Okay, so hopefully the hyperbolic trigonometric functions are much more clear to you, and hopefully they will not possess quite a bit of challenge for you on the exam. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE power exam preparation programs, please visit my website, studyforfe.com.